Hello and welcome to the Swiftbird. I'm Yakov, and in this episode I'm continuing the Swift and iOS Basics series. Last time we talked about value and reference types in Swift. While we mostly focused on the differences between them, in the end of that video I mentioned a feature that brings them closer together. That feature is called Copy on Write, and today I invite you to explore it in detail. I'll explain how it works, highlight its benefits and drawbacks, and demonstrate how you can implement Copy on Write for your own types. If you find this video helpful, give it a thumbs up, and subscribe to the Swiftbird to stay tuned for future episodes. As you remember from the previous video, value and reference types, specifically structures and classes, they have quite a lot in common. You can use either to store data and perform actions. What makes them different is how they work behind the scenes. In that video, I called value types a good choice for most tasks. That's because they're fast, versatile, and easy to manage. Reference types have a few unique properties, such as inheritance. But when you don't need them for a task, you'd be better off with value types. Because the more tools you have at your disposal, the easier it is to make a mistake. One thing value types aren't that good at is storage efficiency. Remember, structures store their data on the stack, which in theory makes accessing it faster. However, using the same data from multiple places isn't very straightforward. Moreover, when you try to copy a variable that points to a value type instance, its data gets copied right away. In most cases, that's exactly what you want, because when you have a separate data copy for each variable, you don't risk accidentally changing the others. But as you can imagine, duplicating data every time is not quite efficient. That's especially true for large objects. For example, imagine you've got an array that holds 1,000,000 elements. You pass it to a function that maybe takes every other element. Or maybe that's all the elements together. It doesn't make a lot of sense to copy every element in this case, does it? In that scenario, you don't modify any data, so there's no risk of unintended changes. The function parameter could perfectly have used the same data instance that already exists. Now imagine a different situation. You've got the same array with 1,000,000 elements, but now your task is to reverse them while keeping the original object intact. You obviously need a separate copy in that case, otherwise you'll mess up the data. Wouldn't it be nice if the system somehow knew when it's safe to reuse the data in memory? Copy on Write, or COW, is a feature that does exactly that. In a nutshell, it's an optimization technique created specifically for value types. Copy on Write lets you defer the copying of objects until it's really needed. As you've seen in the examples, really needed basically comes down to when you want to modify data. And that is the main principle of Copy on Write in Swift. The underlying data of value type objects can be shared between multiple references, as long as none of them needs to modify it. Only when a reference tries to change the data, a separate copy is created. The best thing about Copy on Write is you're getting it for free for many built-in types. That includes collections such as array or set, where the benefits are most noticeable. You may be using COW right now without even realizing that. But it's important to note that Copy on Write is not something that can be inferred behind the scenes. Each type has to provide its own implementation. Later in this video, I'll show you a way of implementing Copy on Write for your own structures. But before that, I'd like to highlight the advantages and, most importantly, drawbacks of Copy on Write. As you'll see very soon, this mechanism is not a silver bullet, so using it with every type in your app is perhaps a bad idea. As its name implies, Copy on Write is designed to reduce memory usage by creating copies only when you really need them. This improves efficiency, especially for large data structures. You probably know that iOS keeps track of the apps sitting in the background. If some of them are using too much system resources, iOS terminates them. So reducing the amount of used memory comes with the added benefit of fewer terminations and fewer subsequent cold starts. To the user, your app feels more responsive. Performance boost is another benefit of using Copy on Write, even though it may not be very noticeable when your app runs on the latest device. But no matter how powerful your device is, copying operations are still expensive. So by delaying them until absolutely necessary, you save bytes and clock cycles. But Copy on Write is not without drawbacks. This mechanism shines when your data is mostly read-only. In that case, it helps you avoid excessive duplication. However, if your data undergoes frequent changes, copy on write doesn't make much sense, because your objects will be copied every time. This use case basically defeats the whole purpose of Cow. Another downside of copy on write is the overhead. Creating copies of large objects can be expensive, and in performance-critical scenarios, this can become a concern. You may argue that, with or without copy on write, copying data has the same cost. And you're right. But the difference lies in predictability. Copy on write behavior is hidden within the standard library, which makes it less transparent even for built-in types. Imagine you created a snapshot of an object just to modify it later. Without copy on write, you can pinpoint the exact moment when duplication takes place. It's right here when the second variable is declared. But with copy on write, things become more obscure. You expect copying to occur when you change the second object. In reality, though, you don't have that guarantee. What if somewhere in between these lines the first object changes? That would trigger copying just as well. And if it happens to take place in the middle of some time-critical operation, you may get surprising results. And by surprising, I mean disappointing. It won't be something terrible perhaps, but you risk spending a lot of time reasoning about memory usage and optimizing the code. However, something terrible can happen if you're not careful enough when you implement copy on write yourself. Cow can make your code vulnerable, and this will be so subtle you may not notice anything. The most common reason for those problems is when multiple references are still pointing to the original data, when you think it's been duplicated. As you can imagine, debugging memory issues is never an easy or pleasant task. You know that saying about where good intentions can lead you. So the key takeaway from this part is that you better be conscious when you decide if you need copy on write. This is not a universal hack, and you can't assume your custom structs will always benefit from Cow. Otherwise, this mechanism would have been implemented for all objects by default, or at least I think so. But if you evaluated your situation, decided that you do need copy on write, and you feel confident that you can implement it correctly, then welcome to the next section. Okay, let's implement copy on write for our custom types. As you can see, here I have my user struct. It's very basic, has only one property, and doesn't include the copy on write behavior. That means its data will be copied as soon as I create my second variable. But I want its data to be copied only when I change some of the properties. The most common way to implement copy on write involves two helper objects. One of them is a reference wrapper. Basically, it turns our value type into a reference type. This is important because copy on write relies on reference counts, and value types don't have them. Here I added my cowref class. It's very simple and there's not much to say about it. But the next helper object is really important. It is the core of the copy on write implementation. If you search copy on write on the internet, you will most likely find something like this. It's a wrapper or a box which holds a reference to my value type object. But it also performs one important thing. It checks whether my reference object is referenced from only one place or from more than one places. Basically, that's the entire mechanism of copy on write. When there's a call to change something in the object, the wrapper checks if it's safe to do so directly or if it should create a separate reference. So this isNownUniquely referenced call is the secret ingredient of copy on write. If my object is referenced from only one place, then I can update its data directly. Otherwise, I'll create a separate reference. And that's it. Let's update the test code. Basically, I just wrap my user object in a cow box. And you can see that I have to update other parts of my code as well, but we'll get back to it later. Let's see if it works at all. I've set a breakpoint just before my data is going to be mutated. I'll run my app and see how many reference instances there are in the runtime. I open the memory graph and basically just search for my reference object. And that is the easiest way to see if it works. Some copy on write implementations you can find on the internet suggest that you try to print the address. But I found this to not work in every case, so I'll continue using the memory debugger. Before I change my data, I have only one reference. Now let's move the breakpoint and see if there's a new object created after I change the data. And yes, as you can see, after I performed my write operation, there's a second reference object. That means the data has been duplicated. But you can also see that this method of implementing copy on write is not very elegant. It involves changing lots of places. So my approach to handling this would be to change this box wrapper into a property wrapper, just to make accessing the data a little bit more transparent to the code. I'll declare a very simple property wrapper, and basically I'll just move the existing code from the cow box. And when I update my test code, you can see how much cleaner it becomes. But there's a problem. So far, user1 refers to my user object, not the property wrapper. That means when I create my user2 object, it copies the data immediately. And that is not what I want to do in this copy on write tutorial. To fix this, let's add another initializer to my property wrapper. And this time, it will take another property wrapper object. This method will basically just copy the reference without duplicating the data. I'll add a projected value so I can reference the actual property wrapper. And with one small update to my test code, I should have copy on write work again. Ah, right. The compiler doesn't know which initializer it should use. I can fix this by specifying the type explicitly. But I don't really like this solution, because it makes errors very likely. Instead, I'll update my second initializer. And also, I'm gonna have to update my test code, but only a little. So now I should have copy on write work once again. Let's go ahead and test it. Before any changes, I have only one reference, but once I change the data, I should have the second one as well. As you can see, with this property wrapper approach, we were able to get rid of those extra value calls. So implementing copy on write like this makes applying it less invasive. Okay, but you may ask, what about those arrays or sets or dictionaries? I don't remember using property wrappers or box objects with them. You're right. That's because the copy on write implementation is hidden within those types themselves. Can you do something like this? Absolutely. But I gotta warn you, this ain't gonna look very nice. So let's go ahead and update our user struct to encapsulate the copy on write mechanism. I'll create an internal structure that holds the actual data, and the existing user struct will provide the interface and the cow implementation. Just as before, my data will be wrapped in a reference object. The initializer will take just a name parameter and create both the internal user and the reference behind the scenes. It will also expose the name as a computed property. The setter will have the same code as before, just with one change. In its else branch, I will duplicate the existing user, change its name to the new value, and retain this new object by reference. So that's it. Just a little refactoring to hide the internals. I no longer need the property wrapper, so I'll remove it. Now it's time to update the test code and see how it works. The debugger shows just what I expected. Here's my test code again. It is exactly the same as in the beginning of this demo. That means my encapsulated copy on write implementation doesn't affect the client code in any way. That is a good thing. But the bad thing is this approach doesn't scale well. You can implement copy on write like this for a couple objects with a couple properties, but then it becomes really hard to maintain. Also, keep in mind that all copy on write implementations I showed provide zero thread safety. So think twice if you really want to deal with this. So, that is Swift's copy on write, a little trick that brings value and reference types closer together. I explained how it works, how you can implement it for your own types, and when it makes sense to do so. But remember, copy on write is definitely not something you should worry about in your day-to-day work. It's totally fine to use value types without cow. In most cases, you won't be missing anything. Personally, I don't bother with copy on write unless I absolutely need it. And even then, I first turn my attention to less error-prone solutions. So for me, copy on write is mostly a fascinating concept that highlights the flexibility of Swift. That wraps up today's episode. If you found it helpful, I'd really appreciate you giving this video a thumbs up. Subscribe to the Swiftbird to stay tuned for future episodes. I'll be back with more tech stuff soon. Until then, make your copies fly.